Hello everyone, welcome to this video lesson. In this video lesson, we would like to derive an equation for electric potential at different points of a spherical shell, which is similar to that of a conducting sphere, because a conducting sphere always pushes the charges onto the surface of the sphere. Similarly, the spherical shell also always puts the charges on the surface of the shell. So both the derivations are same. So let us consider a spherical shell whose radius is equal to r, who is having a charge q. We want to know the electric potential at different points. So let us consider a point P who is outside the spherical shell. So let us say case 1, when point is outside. That means the location of the point is greater than the radius of that spherical shell. We know, we have already derived that due to a spherical shell, electric field intensity is 1 by 4 pi epsilon naught q by r square. It simply behaves as if like a point charge for an outside point due to a spherical shell. You know E now, you want to calculate V. You know the formula, electric field intensity is minus dV by dr. So dV equal to minus E dr. So V equal integral of minus E dr. E value we have already derived, 1 by 4 pi epsilon naught q by r square and dr. So minus q by 4 pi epsilon naught is constant, integral of r power minus 2 dr. Simplifying that further, voltage at a point outside the shell is minus q by 4 pi epsilon naught r power of minus 2 plus 1 by minus 2 plus 1. We know the formula for integral of x power n dx is x power n plus 1 by n plus 1. So that is minus q by 4 pi epsilon naught r power minus 1 by minus 1. This minus and this minus will cancel, so the remaining value is 1 by 4 pi epsilon naught q r power minus 1 and the denominator is r. So the expression is similar to the potential due to a point charge itself. So when you are talking about a point outside the spherical shell, the entire charge behaves as if like it is focused at the center of the spherical shell. So if we have to talk about case 2, on the surface of the spherical shell, everything is same, where the distance of the point small r becomes capital R. So potential becomes 1 by 4 epsilon naught q by capital R, that is outside. Let us write about case 3, inside the spherical shell. That means R value is less than that of R. We know the formula, inside a spherical shell, we know all charges resides on the surface of the shell. So charge inside shell is 0. As charge is 0, automatically electric intensity inside the spherical shell is also equal to 0. We know the formula, E equal to minus dV by dr, but that is 0 inside a shell. So dV is also equal to minus 0 into dr, that is equal to 0. So there is no change in voltage. That means voltage is constant, and that is equal to voltage at the surface. That is the same value that we have derived on the surface, 1 by 4 pi epsilon naught q by r. That's how electric potential varies in a spherical shell. So if you try to draw a graph for the variation of electric potential, taking the distance on x-axis, potential on y-axis, inside a spherical shell until the radius, potential remains constant, that is 1 by 4 pi epsilon naught Q by R. Outside the spherical shell it decreases this way, 1 by 4 pi epsilon naught Q by R. This is how voltage and varies with distance in the case of a spherical shell, which is similar to that of a conducting sphere too. Thank you for watching. Keep coming back for more and more video lessons. Thank you.